Everybody, thank you. Thank you again for the introduction. I'm Shelley. I'm a software engineer at GitHub working on open source. Today, I would like to do a deep dive into the mechanics of asynchronous programming in JavaScript. To make sure we're all on the same page, before I really get started, I'll go over basic principles of async. Then, we'll launch into the different methodologies and the nuances of what exactly differentiates them. And then finally, we'll compare over the spectrum of options to discuss which situations require which approaches. Let's say you have a program contained within a single file. It's made up of functions, and at any given time, only one of these is going to be executing now. The rest will execute later, at some point in the future. That, there, is the crux of async. It's the relationship between now and later, and the way in which you manage this relationship with your code. What is key here, however, and what causes some of the most difficulties for developers when they're just starting out, is that later does not mean strictly and immediately after now. It could be at any point in the future, and you don't necessarily know when that will be. Now, let's move on to some of the technical underpinnings of how code is executed in the JavaScript environment. In pursuit of this understanding, it's best to start with the event loop. The event loop can best be conceptualized as an endlessly running, singly threaded loop, where each iteration runs a small chunk of code in the program. If you wanted to run a chunk of code at a later time, that chunk would simply be added to the queue for the event loop. And when the time came that you desired it to execute, it would be dequeued and executed. With ES6 came a new concept called the microtask queue, but we'll save that for a little bit later. It's also important to mention that JavaScript has what's known as run-to-completion semantics. This means that the current task always finishes before the next task begins, or until it explicitly yields control back to the event loop. As a result of this, each task has complete control over all current state and does not need to worry about another task modifying things at the exact same time. Looking at the code here, running this will always print first and then second, because the function starting and set timeout is added to the task queue immediately, but is only executed after the current piece of code is done, since it yielded control. Now, let's take a look at the call stack. When a function foo calls a function bar, bar needs to know where inside foo to return to after it's done. This information is managed with the call stack. Take a look at the set of 3 functions on the left-hand side of the slide, and let's walk through how the stack will look as the program executes. Initially, when the program above is started, the call stack is empty. After foo is called, the stack has one entry, location and global scope, so that, as I mentioned before, foo knows where to return to when it's finished. Next, after bar is called, the stack has 2 entries. It's now stored the location that bar needs to return to when it's finished executing, in addition to global scope. The trend continues as baz is called, and the stack now contains baz's return address, as well as the previous return addresses from previous function calls. When console.log is called in baz, the call stack is printed to console. Next, each of the functions terminates, and each time, the top entry is removed from the stack. After foo is done, we're back in global scope, and the call stack is empty. At the end, we return, and the program is terminated. In looking at this, you can see a handful of the things I previously mentioned: the event loop, the task queue, and the stack. The current task comes off of the event queue, and its location is stored in memory, while relevant variables populate the heap. The task queue is populated by task sources, any one of which would be a particular chunk of code in an executing program. This snapshot would represent the moment after all functions in the previous slide had executed and before locations had begun to pop off of the stack. Most of you have likely encountered callbacks, so I'm going to focus more on how they fit into the async landscape as a whole. Let's start by looking at some functions and discussing them in context. Here, you can see I have two programs side by side. On the left, the function names are alphabetical from top down, and on the right side, I've mapped the functions to the order in which they run. Most likely, your eyes have to do a significant amount of jumping around in order to discern the order in which the functions are executing for the program on the left, since they're not running in the top-down sequential order in which you might expect. By following the cardinal number words on the right side, you probably had an easier time. So let's talk about why that is. Your brain operates sequentially, which places it at odds with the inherent functionality of callbacks. This is a comparatively simpler example, but when callbacks start to next significantly, you enter what's known colloquially as callback hell, which becomes progressively more difficult for your brain to reason through. What's happening here in terms of the call stack, and by extension, the event loop? Assuming all these functions are async, first we'll begin, and then immediately yield control, and then second, we'll execute. A callback was registered by first, so the next available task will be that callback. Next, third will execute, followed by fourth. Fourth registers a callback, and then returns control, so that fifth executes. The callback registered by fourth will come off the queue and execute, and then finally, sixth will execute. For each of these functions taking a callback, the callback itself is a black box for the function. The continuation of the program is dependent on our handing that callback off to another part of the code, and then essentially just praying that it'll do the correct thing when the callback is invoked. This paradigm is known as inversion of control and can create significant trust issues. In the previous code snippet I had up, you could see that your eyes had to skip around, even though they most likely wanted to read the code in a top-down fashion. When you sometimes struggle to understand how and when each part of a piece of code is working, it's undoubtedly hard to deal with errors in that code. Within the callback landscape, there are two ways in which errors are reported, via callbacks and via exceptions. You need to be careful to combine both properly. This is because the most obvious, but occasionally overlooked aspect of dealing with errors in callbacks is to make sure that they've actually all been handled. However, there's a caveat to this advice, and it lies specifically in how errors are caught. Can you see how in the snippet above, I returned and didn't throw an error? That was intentional, because exceptions are only a synchronous mechanism, which is logical. In an asynchronous environment, the exception could be thrown, and when the handler block is already out of scope, the error would be rendered meaningless. The next big innovation in asynchronous programming, promises, hit JavaScript with ES6. Before this, there was no direct notion of async built directly into the JavaScript engine. All it ever did was execute a single chunk of your program at any given moment when asked to. You, the developer, asked it to by means of callbacks or timeouts in order to shuffle its place in the event loop. With promises came a change to the JS engine, which took a form of the queue I mentioned very briefly at the very beginning, the microtask queue. Before I delve into how exactly this changes the form of the stack queue event loop diagram I showed you a few slides ago, let's look at an example of a program utilizing promises and then discuss what's happening and why. Promises act as placeholders. They allow us to reason about future values without necessarily knowing their outcomes, making them functionally extemporaneous. When the future value is settled, it might succeed or fail. And then at that point, the promise is no longer a placeholder and becomes an immutable value. A few slides ago, I referenced a paradigm known as inversion of control, where we handed off callbacks and just hoped they did the right thing. Promises confer to us a capability to know when a given task finishes, and then our code can decide what to do based off of those results. Importantly, promises may seem like an entirely different paradigm, but in fact, they don't get rid of callbacks at all. They just change where the callback is passed to, and remove the black box effect we saw previously. We get back from a function the ability to know when it's completed, and then perform new tasks from there, as I said. Promises are not just a mechanism for single-step operations that follow with this, then that flow. They're capable of that, of course, but it turns out that we can string multiple promises together to represent a sequence of async steps. This ability is conferred to us as a result of two key characteristics of promises, which are that, one, every single time you call .then on a promise, it creates and returns a new promise. And two, the value returned from the .then's call's fulfillment callback, the first parameter, is automatically set as the fulfillment of the chained promise. Looking to the slide, by returning hello world, we fulfill the promise that the first .then call created and returned. When the next .then call runs, it's receiving the fulfillment from the returned hello world statement. The second .then would create then another promise. So, how does this look under the hood? Promises utilize the microtask queue, which allows us to say, here is this thing that I need to do later, but I need to ensure it happens immediately later before anything else can happen. The microtask queue can best be thought of as attached to each tick in the event loop. Some async actions will be added to the end of the current tick's microtask queue, instead of creating a whole new tick in the event loop queue as a whole. When promises are resolved or rejected, the associated handlers will be called asynchronously as microtasks, and then added to the queue for the current tick. This diagram looks nearly identical to the diagram I showed you a few slides back, with one key difference, the addition of the microtask queue. Once a promise settles, or if it's already settled, it queues a microtask for its reactionary callbacks. This ensures promise callbacks are async, even if the promise has already settled. So calling .then with resolve or reject against a settled promise immediately queues a microtask. Any additional microtasks queued during a given microtask are added to the end of the queue and also processed. So, in looking at the diagram, you'll see that the current task can come off the task queue or the microtask queue. All promise callbacks are queued as microtasks. A microtask can also cause one or more microtasks to be added to the end of the same queue. So it's theoretically possible that a microtask loop could spin indefinitely, thus starving the program of its ability to move on to the next event loop tick. This would conceptually be almost the same as expressing an infinite loop in your code. What happens if something goes wrong in a promise? How do we deal with those errors? By default, it turns out, promises are silently swallowed if they're unhandled. More specifically, any exception which is thrown inside a .then, within a .then handler, or within a function passed to a new promise, will be silently disposed of unless manually handled. The standard way to handle errors from promises is to add a catch handler at the end of your promise chain. You can also chain these handlers so that you can throw errors into progressively more outer-level scopes. Catching and rethrowing errors in this way will tell you what led to the error more effectively so that you can later debug the issue more efficiently. If exceptions are thrown inside the callbacks of .then and .catch, it's not necessarily a problem, because these two methods convert them to rejections. Let's look at an example and talk about what would work and what wouldn't in more concrete terms. This is a simple promise example. And from looking, you can see that prom is going to reject with an error no matter what. So what happens in the first example versus the second? The first has a catch. So it's going to print the error, followed by the error message, which in this case is rejected. You can also see the associated call stack by printing error.stack. The second one doesn't have a catch. So even though it threw an error, it'll simply fail silently. This next type of async approach, generators, sits a little on the edge of the overall async landscape, but is nevertheless important to touch on. The first thing to observe as we talk about generators is how they differ from normal functions. There are several notable differences, but key to generators is their behavior with respect to the run-to-completion expectation. With generators, we have a different kind of function, which can be paused in the middle either once or several times. It is resumed later, which allows other code to run during these pause periods between runs. The main strength of generators is that they provide a single-threaded, synchronous-looking code style, but allow us to hide the asynchrony away as an implementation detail. This lets us express naturally what a program's step and statement flow is, without having to navigate the asynchronous gotchas and syntax at the same time. To get a better idea of how this looks in practice, let's see a function. Here, you'll see immediately that there's a little star next to the function in the signature. This is the syntactical indicator that you're looking at a generator function. The keyword yield will send out a value whenever the function is run. So here, the yield index ++ expression will send the index value out when pausing the generator function at that point. If ever the generator is restarted, whatever value is sent in will be the result of that expression, which will then get added to 1 and assigned to the index variable. When we start, index is 0. So this will be yielded, and then 1 will be added to index as a result of the ++. This will occur each time as the value of index is passed out and then in again, and so that it increments by 1 every time. To see this a little more clearly, let's look at a diagrammatical representation. On the left, you'll see a traditional non-generator function. It adheres to the run-to-completion behavior we expect from functions, with no interruptions from beginning to end. On the right is the generator function, with multiple stops and starts between beginning and end. It's important to note that there's no real official end, per se, in a generator function. The end, in this case, would just be the last time that yield is called. When the generator function is initialized, an iterator is returned, and then the generator starts with the first call to next on the function. This function pauses when yield is called, and then would restart with the next call to next, and so on and so forth. To recap, with normal functions, you get parameters at the beginning and a return value at the end. With generator functions, you send messages out with yield, and you send messages back in with each restart. One of the most powerful parts of ES6 generator design is that the semantics of the code inside a generator are synchronous, even if the external iteration control proceeds asynchronously. That's a fancy way of saying that you can use a very simple error handling technique you're probably familiar with, the try-catch mechanism. Even though the function will pause at the yield3 expression and may remain paused for an arbitrary amount of time, the try-catch will catch it. With normal async capabilities, like callbacks, that's almost impossible to do. The generator itself also has a throw function to throw an error into the generator at its pause position, which of course can also be caught by a try-catch inside the generator. Async await is a new way to write asynchronous code. Previous options are callbacks and promises. Async await was created to simplify the process of working with and writing chained promises. And so async await functions themselves return promises. They cannot be used with plain callbacks. Async await is thus, like promises, non-blocking, and makes asynchronous code look and behave more like synchronous code. This is where all of its power lies. Since any async await function returns a promise implicitly, the resolve value of the promise will be whatever you return from the function. To illustrate, let's look at code. Here, we're returning a string that contains several components of a street address. The function has the async keyword before it, and the await keyword can only be used inside functions defined with async. all 4 variables must be resolved before the function will return the desired string. Also important to note here is that if we did not use the await keyword before each of the address component functions, this function would not necessarily fail. It would just mean that the variables would be set to promises instead of the values returned from them. There is also an oft-overlooked gotcha I'd like to point out here before I move on, which is that await calls operate sequentially. What this means is that the call to get city won't kick off until after we have a value for get street address. In some cases, this is desired behavior, such as when one call depends on the results from a previous call. Here, however, we want to get all of these address components simultaneously, so we shouldn't be blocking each on the previous one. Instead, we should rewrite it like this. Under the hood, async await works almost exactly the same as promises, utilizing the new microtask queue introduced to handle async operations. If you're familiar with promises, you know that if a promise is rejected, you need to handle that error inside a catch. And if you're handling errors for both synchronous and asynchronous code, you will likely have to duplicate your error handler. In the above snippet, we can see that there's duplicate code on line 6 and line 8. The catch statement on line 7 will handle any errors that the synchronous function do synchronous things may throw. But it won't handle any errors thrown by do something since it's synchronous, or since it's asynchronous. My apologies. This example may seem palatable, since all it's doing is printing the error to console. But if there's any kind of complex error handling logic, we want to avoid duplicating it. Async await lets us do exactly that. By looking at the code snippet on the top right, you'll see that we only catch once. When we use async await, we can catch errors from both synchronous and asynchronous actions in a single handler. Here, we can both minimize the total amount of code that we write and catch errors in a more readable and clear way. So, wrapping up. Our brains plan things out in sequential, blocking, singly threaded, semantic ways. But callbacks express asynchronous flow in a rather nonlinear, non-sequential way, which makes reasoning properly about such code much more difficult. Callbacks suffer from lack of sequentiality and lack of trustability. But they're good in situations where you may just be performing a simple request that's always asynchronous. They're just plain functions, so they also don't require any additional understanding beyond knowing how asynchronous operations work. They also tend to be more verbose, so coordinating multiple asynchronous requests with them concurrently can lead to callback hell if you're not actively modularizing your functions. Dealing with errors also tends to be more confusing, since there could be many error objects that all go back to a single error further down the call stack. Promises are easier to reason about, although they still have their downsides. They're especially useful for coordinating multiple asynchronous operations, propagating errors from nested async operations, and dynamically chaining asynchronous operations, i.e. those where you would do something async, examine output, and then do something else async based on the intermediate values. Errors and error stacks in promises can also be a challenge, because they can behave unintuitively in the way in which they print errors when those errors are thrown. They brought new changes to the JavaScript engine and paved the way for later innovations like async await. This latest async pattern is essentially syntactical sugar on promises, but it allows for more intuitive reading of asynchronous code. It also improves error handling compared to traditional promises, and can be handled with simple try-catch blocks. It's so easy to use async await that one of its slight dangers is that you forget that you're writing asynchronous code at all. Ultimately, the best tool to use for a job is going to be the one that's most specific to the job that you're doing. But now, I hope you'll have a firmer grasp on what exactly makes each of these tools a best fit for certain jobs, and be able to use them with the deeper understanding of what's going on at a granular level. Thank you very much.